Now let's compute simplicial homology of the torus. Let's argue geometrically first, and then we'll do computation. So the torus has only one connected component, and thus H0 must be Z. Now it has two one-dimensional holes, so H1 must be Z plus Z, and then because the torus has one two-dimensional hole, H2 must be Z. Finally, since it doesn't contain any higher dimensional simplices, its higher dimensional homology groups are all trivial. Alright, so that's the geometric argument. Now let's actually compute this. To do so, we need to put on it a delta simplex structure. So let's use the following triangulation. With respect to this triangulation, the torus has one vertex, three edges, and two faces. Now to compute the homology groups, we need to know the boundary maps. Obviously, this D0 is 0, but conveniently, D1 is also going to be 0. Thus, H0, being the kernel of D0, quotient now by image of D1, must be Z, because the kernel of D0 is everything, it's all the zero cycle. And the image of D1 is just 0 because D1 is a trivial zero map. So there are no boundaries, and H0 is isomorphic to the group of zero cycles and thus isomorphic to Z generated by V. But now our luck ran out. The next map D2 is no longer 0, but it's not too bad. How do we find this formula? Well, here let's practice reviewing the definition of the boundary map a bit. So we want to look at the torus before identification, and then order the vertices. Recall that orientation on edges should be going from the vertex with the smaller index to the vertex with higher index. So then this should be the one with the smallest index. So we'll call this V0, then V1, V2, and V3. Then by definition of the boundary map, we have that the boundary of the face F is just gonna be this alternating sum of edges, and that's just gonna be equal to B minus C plus A. You can easily calculate that the same things hold for G. Now let's compute H1. So H1 is gonna be the quotient of kernel of this D1 over image of D2. Now what's kernel of D1? Remember, D1 was the zero map, so kernel is this full group of one chain. So it's going to be the free abelian group generated by ABC. Alright, so now what's the image of this D2? Well, we just computed that a moment ago. That's going to be generated by A plus B minus C, so this quotient is just going to be the abelian group on two generators with no relations, and that's going to be isomorphic to Z plus Z. And now finally, let's look at H2. H2 is the kernel of D2 modeled out by the image of D3. But D3 is just the zero map, so this denominator here is just 0. Now what's the kernel of D2? Observe that the image of a one chain under D2 is just going to be of this form. So this one chain lies in the kernel if and only if M is equal to minus N. And thus the kernel is going to be generated by F minus G. Thus this H2 is free abelian group generated by one element, so that's going to be isomorphic to Z. So look, the homology groups are exactly as we have anticipated. That's good because they are supposed to capture the topology. Alright, so let's move on.